There's nothing new under the sun. That's what people always say, especially when it comes to the arts. Everything's been tried before. But I don't think that's true. In fact, maybe the opposite is true. What's been done already is actually minuscule, even infinitesimal, when compared with what hasn't been done. Regardless of how long the human race ultimately survives, it could be said that we are still in our infancy, and we will always be in our infancy in our exploration of the infinite world of possibilities. I mention this now because I'm about to introduce a completely new way of composing music, and I know that there'll be skeptics out there who won't believe that it's possible for such an undiscovered method to exist, that there could still be whole continents and even planets still waiting to be explored. So first of all, what is the golden ratio? It was first written about by Euclid in about 300 BC. He wrote that there is only one place on a line where you can cut it so that the ratio of the larger piece to the smaller will be equal to the ratio of the whole line to the larger. And that ratio is roughly 1.61803, what we now call the golden ratio. And it's often symbolized by the Greek letter phi. So that means that the golden ratio is roughly 161.8%. And there are all sorts of interesting mathematical phenomena involving the golden ratio. For example, it's present in all pentagrams and pentagons. And many, many claims have been made about it in relation to nature, art, music, and virtually everywhere else you could imagine. As it turns out, a lot of these claims are highly questionable. But nonetheless, there are certain phenomena that do unquestionably conform to the golden ratio. What do they all have in common? They all have repeating patterns, and, as we'll see, these patterns contain many proportions that are in the golden ratio. And it's possible that maybe the golden ratio's mathematical and aesthetic significance increases the more times it's present within a system. But what does any of this have to do with music? Bear with me just a little longer, because this method is based on trees, in particular on how certain types of trees grow new branches. So imagine that you're looking down on a tree from above so that the trunk looks like a circle, and say that the first branch grows at 0 degrees the top of the circle. Amazingly, the second branch, spiraling upwards, will grow at roughly 222.49 degrees. This is the golden angle, which is simply the golden ratio of 360 degrees the full circle. The third branch will then grow at about 84.98 degrees, a golden angle's distance from the second branch. And the fourth branch will grow that same angle away from the third. And then the fifth, the sixth, the seventh, etc. So, why this pattern? Well, it just so happens that growing branches a golden angle apart ensures that they will be most evenly distributed throughout the totality of the tree's life, maximizing each branch's exposure to sunlight. No other angle will work as well. And this same method is used by roses when they grow petals, by pine cones, artichokes, pineapples, cacti, and many other types of plants. But now here's the question. Could this method be used to evenly distribute things other than tree branches and flower petals? Say, musical pitches, for example. Let's find out. We'll start by looking at the tree from above once again, but now we'll divide it up like a clock into 12 pieces, and we'll write the 12 pitches of the chromatic scale around it, with C at the top. And now we'll do the exact same thing we did before with tree branches. The first branch is at 0 degrees, which is in the C sector, so we'll write a C. The next branch is the golden angle away from that, at 222.49 degrees. That's within the G sector. Then the third branch is at 84.98 degrees, an E flat. Then B flat, G flat, etc., etc. Now in theory we have an infinitely long list of pitches. So, let's hear what they sound like. If you're like me, you're probably thinking, so what? They just sound like random pitches. But are they? Let's see if we can make some sense of them. Let's start with what's most obvious. Every pitch is either a fifth or a minor sixth higher than the preceding one. First, C goes to G. That's up a fifth. Then G goes to E flat. That's down a major third, which can be respelt as up a minor sixth. And from there on out, they're all either up by fifths or minor sixths. And when you think about it, this makes sense, because the golden ratio of an octave is somewhere between a fifth and a minor sixth, as you can see here. A way to visualize this is to imagine a person walking across a giant piano keyboard, where every stride is the golden ratio of an octave. So what happens when you stack fifths and minor sixths on top of each other? Let's take a look. We'll start with the first three pitches, C, G, E flat. As you can see, they form a simple C minor triad. Now let's move just one pitch further down the chart. That's G, E flat, B flat. That's an E flat major triad. And the next three notes make E flat minor, then G flat major, etc., etc. As you can see, there are lots and lots of major and minor triads in this list of pitches. So here's a question for you. Is this list tonal or atonal? On the one hand, it was derived from tree branch angles, so how can it be tonal? But on the other, listen to this, which is just these chords with a melody played on top of them. It sounds almost impressionist, doesn't it? Not too atonal sounding at all. So now we have our first interesting fact about this series of pitches, the major and minor triads. Are there others? Let's take a look and go back to our original list of pitches. Remember how random they sounded? Let's see what happens if we put some of the pitches in a different octave. And now group them in threes. And add in some bar lines. A little less random sounding. Now let's do one more thing. Let's circle every 12 pitches and listen again, now with the circled pitches delineated by a bass line. Does it sound familiar? It should. That's because the circled pitches form the circle of fifths. What is the circle of fifths? It's simply the circle formed when you go from pitch to pitch by the interval of a fifth down. And it's one of the most ancient and ubiquitous of all chord progressions. Here's a famous example of it in Vivaldi's Four Seasons. There are thousands of other examples because virtually every composer used the circle of fifths. And it's no less prevalent in pop music. Here's a song popularized by Frank Sinatra. Since the Sinatra song and our list of pitches both use the circle of fifths, let's try something crazy and see what happens if they're played together. We'll fast forward to the A at pitch number 108 so they're in the same key. For a while they seem to fit together pretty well. So, our second interesting fact about this series of pitches is the circle of fifths pattern. But I've saved the most interesting fact till last. Let's once again go back to our original list of pitches. But this time, instead of circling every 12 notes, let's just circle all the C's and write down the numbers where they appear. 0, 13, 21, 34, 55, 68, 76, 89, 102, 110, 123, 131, and 144. As you look at this series of numbers, does anything jump out at you? people with a little bit of a math background might notice something. The circled numbers are part of the Fibonacci sequence. So, what is the Fibonacci sequence? It's named after Leonardo Fibonacci of Pisa, who lived a long time ago. And how you get the sequence is really very simple. You start with 1 and 1, and then add them together to get 2. Then you take 1 plus 2 to get 3. Then 2 plus 3 to get 5. 3 plus 5 to get 8, etc., by just adding the two previous numbers to get the next one. And as with the golden ratio, Fibonacci numbers can be found all over the place in nature. One example that you can see really easily involves pine cones. First, you can count the rows going clockwise. In this example, we get 8. Then you can count them counterclockwise, getting 13. And guess what? 8 and 13 are consecutive Fibonacci numbers. And that's true for almost every pinecone that you'll find. So what's the ratio of 13 and 8? It's 1.625. That number looks a little bit familiar, doesn't it? Take a look at how close it is to the golden ratio. Now, as we look at the ratios of all the consecutive Fibonacci numbers, a pattern emerges. They get closer and closer to the golden ratio. Take a look. By the time we reach 144/89, it's accurate to 4 decimal places. What this shows is that the ratio of consecutive numbers in the Fibonacci sequence approaches the golden ratio. This means that Fibonacci numbers and the golden ratio go hand in hand. You could even say that they're almost as closely related as even numbers are to the number 2. So, in retrospect, it's not at all surprising to discover Fibonacci numbers in a list of pitches derived from golden ratio tree branches. And now, as we look at all the numbers where C appeared, there are countless Fibonacci number relationships, even within just the first 144 notes. And what this in turn means is that there are countless golden ratio relationships, never exact but often accurate to many decimal places. And keep in mind that this is true not only for the Cs, but for all the other pitches as well. This is incredible. It means that if you find any two similar places in the pattern and take their golden ratio, you'll find a third place that is also similar, on a micro and macro level. So, can we hear these patterns in the music? Let's listen to those Cs highlighted. I know, it's not that interesting, right? So let's reorganize the pitches a little so that they now reflect the patterns beginning with each C. Just to get a better sense of what's going on, let's look at the first 5 pitches. C, G, E flat, B flat, G flat. When do they appear again? At 13, a Fibonacci number, it seems like the pattern is trying to begin, but it only gets 3 out of 5. At 21, the next Fibonacci number, it tries again, and this time gets 4 out of 5. And then at 34, it's also 4 out of 5. But then at 55, the next Fibonacci number, it finally succeeds in replicating all 5 pitches. What this shows is that the pattern replicates more and more precisely as the Fibonacci numbers get larger. And remember, the golden ratio of 13 is roughly 21. The golden ratio of 21 is roughly 34. The golden ratio of 34 is roughly 55. And of course, the golden ratio of 55 is roughly 89, the next place where all 5 pitches are perfectly replicated. So let's see what this sounds like with those 5 pitches highlighted. Maybe a little more interesting? So now we have our third and final fact about this list of pitches, Fibonacci numbers. But I know what you might be thinking. So what? This is all very interesting on an intellectual level, but how is this music, and how does one list of pitches constitute an entire method? Good question, but we're not finished yet. Let's go back to how we first came up with these pitches, a simple circle with the 12 pitches of the chromatic scale going up around it. If you think for a moment, it was quite arbitrary to put the pitches clockwise going up. We could have just as easily had them going down. And if we do, it has the effect of taking our original set of pitches and essentially playing them backwards. But why stop there? Why did we have to put the 12 pitches around the circle in a chromatic scale? We could have just as easily put them around by the circle of fifths. Or we could divide the circle into 24 pieces and have the 12 notes go around twice. Or we could even divide the circle into 144 pieces and put the 12 pitches around 12 times. Check out the list of output pitches. It's a chromatic scale. And just out of curiosity, what happens if we switch it and put the chromatic scale around the circle 12 times? Amazingly, the output is the circle of fifths. So in some strange way, the circle of fifths and the chromatic scale are inverses of each other when seen through the lens of the golden ratio. But now it should be apparent that there's no reason why the circle has to be divided into multiples of 12. We can divide it into 7 and put the notes of the major scale around it. Or we can divide it into 5 and put the pentatonic scale around it. Or in fact, we don't even need to put pitches around it at all. We can imagine that each pitch is merely a variable that could stand for anything. Rhythms, for example. Or chords. Or pitch intervals. Or we could even put fragments of melody around the circle. Let's see what this sounds like if we start at number 10. And now we can continue the chart from there. And take what we get and put it in a three-way canon, each part in a different octave. Let's see what it sounds like. Now we can gradually change each variable. Keep in mind, it's still in canon. Until we end up back with our original circle with the chromatic scale going up around it. But now maybe we're getting ahead of ourselves. I'll talk about canons and imperceptible change in future videos. For now, let's just stop here and review the 3 interesting facts we found about our original circle using the golden ratio tree branch method. The major and minor triads, the circle of fifths every 12 pitches, and the Fibonacci number repetitions. But now we can make these 3 characteristics more general, so that they apply to every list derived from this method. The first one we can simply call qualitative. This means that we can look at any one of these charts, and using our own powers of observation, we can find interesting features to make use of. Perhaps it sounds very chromatic, or perhaps it sounds jazzy, or maybe it even spells out a simple melody. The second characteristic we can call periodic patterns, because every chart derived from this tree branch method will have seemingly periodic patterns. I say seemingly because the truth is that none of these periodic patterns continue indefinitely, not even the circle of fifths pattern I talked about earlier. This is because the golden angle is an irrational number, and therefore no tree branches will ever grow directly on top of each other. This may seem like a weakness of the method, but in fact it's a great strength, because interest and beauty come from the juxtaposition of the predictable with the unpredictable. And finally, the third characteristic we can call aperiodic patterns. And because we used the golden angle for the tree branches, these patterns will all be based on Fibonacci numbers. This means that all the amazing Fibonacci number patterns we looked at already are universal, and will exist for every list we come up with, no matter what variables we place around the circle or how many pieces we divide it into. In fact, you could even say that this method is a system of sorting variables into golden ratio relationships. And what's amazing is to think that all this richness and all these beautiful patterns are derived from nature's method of most evenly distributing tree branches in order to maximize their exposure to sunlight. So as we now come to the end of this video, we've only really scratched the surface of how the golden ratio method works. In the next video, I'll explain how to take the list of pitches derived from tree branch angles and actually make a piece of music out of them, since obviously there has to be more to it than merely playing them verbatim. And in future videos, I'll also discuss other fascinating aspects of the method. I'll talk about palindromes and fractals, both of which were hiding in plain sight in every list of pitches we just looked at. And I'll discuss the quality of Fibonacci-ness, which is actually more important than whether numbers actually are Fibonacci or not. I'll talk about sequences other than the Fibonacci sequence, such as the non-Fibonacci sequence. I'll talk about what happens if you use this method with irrational numbers other than the golden ratio. I'll talk about golden ratio numerology and common myths, including the myth of the golden section. I'll talk about the possibilities for the golden ratio method in the visual arts and possibly elsewhere. And lastly, I'll look at some of my own compositions and show how I went about writing them. I hope you enjoyed this video, and I hope you'll agree with me that this is an exciting new frontier. Who knows where it could lead?